All right, today we're going to be starting chapter 16. So this is the chapter on sound and hearing. Now, this chapter, we're not really going to use too much that we cover in this chapter in later chapters. So it's a little bit different than chapters 14 and 15 in that sense, where we will be using the material from those chapters quite a bit. So this one's a little bit of a more of a standalone chapter, but it still relies on the stuff we learned in chapters 14 and 15 as well. Okay, so let's talk about sound waves. So as we said before in our previous lecture, that sound waves are a type of longitudinal wave, and they're the most common type of longitudinal wave that you'll encounter on your day-to-day life, since all of sound is a longitudinal wave. And sound waves are created by differences in air pressure, or within whatever medium you're looking at. So you can have sound waves in water, sound waves in solids, sound waves in air is obviously the most common. And also a sinusoidal sound wave is the simplest one that we're going to look at today. So a sinusoidal sound wave will have a definite frequency, a definite amplitude, a definite wavelength. And typically when we're talking about sound waves, we want to talk about sound waves in what's called the audible range, sound waves that a human ear can hear. So those are typically within 20 to 20,000 hertz are typically what a human ear can pick up. And for reference, some dogs can hear all the way up to 67,000 hertz. So that's significantly higher than we can hear. All right, so let's look a little bit more closely at sound waves and how they're created. So we saw this same image before when we were talking about different types of waves. So this is our standard longitudinal wave in one dimension. So here we have like snapshots at different times going from t is equal to 0 down to one full period. So we're looking at one full cycle of our longitudinal wave. So you can see here that the wave will move sort of as we're moving through time. The wave is also moving down the tube here. So each particle in the medium is moving parallel to the direction of wave travel. So that was obviously different than when we had transverse waves where they're perpendicular. Now we have that they're parallel. All right, so if we look closely here, so you can see each individual particle, as we said, is moving parallel, so it's moving this way. So this particle here, this is in an area that's getting compressed, right? Because we could see this area is a little bit darker, so this area is getting a little bit more high pressure. It's getting compressed more. So this particle here will oscillate a little bit this way, and then it will oscillate back that way, and then it will get to its original position back here. And these particles will oscillate according to our wave function that we found in the previous chapter. So the displacement of any particle in our medium will be according to this wave function that we have here. And this A here is our displacement amplitude still, so that's given by this amplitude here. So it's just how much is this particle getting displaced from its equilibrium. That's going to be the amplitude now. And you're going to have still a K and an omega. And now the important thing here is to realize that this y now is no longer like a separate direction. It's not actually a perpendicular y direction like we had before. This y is in the same direction as x. So I know that can be a little bit confusing, but it's just to differentiate the displacement y from the position x. So each particle is at a position x along this x-axis here, and then the displacement along the x-axis we're giving by y now. So just be careful to take that into account when you're thinking about longitudinal waves. Here our x and y are like in the same direction. Okay, so we said that these longitudinal waves are propagated basically by via pressure differences in our medium. So we can quantify the relationship between our displacement and the pressure difference. And that relationship is given by this equation here. So this is our pressure difference. So that's the pressure difference from the equilibrium pressure. So let's say in this tube, before we started, putting a sound wave through it, there was some, let's say 1 atmosphere of pressure. This P of xt denotes the difference from that equilibrium pressure. So we have that pressure difference is given by negative B dy dx. So the partial of our wave function here with respect to x. And B here is called the bulk modulus. So now I don't know if in one of your previous classes you did chapter 11, which goes into elasticity. But if you didn't, you don't need too much, you don't really need to know much about the bulk modulus. It's just a measure of how easy or hard something is to compress. So the larger the bulk modulus, the harder something is to compress. So it's just a number that you can look up. So if we have any problems where we're talking about air or water, whatever, you just look up the bulk modulus of air or water, and you just plug that in here, and that's it. That's all you need to know about it. So this is how our pressure differences, that's actually like transmitting the wave, and our displacement along the x-axis of each individual particle are related. So let's just see this a little bit more closely here. So we're looking at all along the x-axis at time t equals 0. So you can see here you're going to have some particles that are displaced the maximum amount, right? So they're displaced, let's say, the maximum amount to the right. And then you're going to have other particles that are displaced the maximum amount to the left. And then you're also going to have some particles that aren't displaced at all, right? You can see here the particles here, 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 and here, they're not displaced at all. So we're going to talk about those a little bit more carefully in some of the coming slides. But that's important to keep in mind, is that some particles are displaced more than others. Just like we saw in our standing waves, there were some nodes and antinodes, where the antinodes were displaced the maximum amount, right? And then the nodes weren't being displaced at all. So we have something similar for longitudinal waves. And now we can see that here, that let's say here, this is our, so this is like a drawing of the individual particles, not a plot anymore. So we have some particles here. So the white particles represent the equilibrium position for each particle. So when they're undisplaced and there's no sound wave, each particle is just sitting here and they're evenly displaced. There's one pressure in the tube, and that's it. And then as the sound wave propagates through this tube, some of the particles will be displaced. And now you have a couple particles here that are at this, correspond to these positions, right? That are not being displaced at all. So they stay actually in their equilibrium position. So these particles that are in the maximum like pressure and the minimum pressure here, you're going to see they're not actually being displaced, right? So like this one, you can think the particles on each side are like coming together and pushing on it equally from both sides. So it's not going to move left or right because it's having, equal force from both sides. And then the same thing happens here in this area of least pressure, because the particles on either side are moving away from it. So it just stays right there in the center and it doesn't move to either side. But all the other particles, so all the particles here and here, 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 and here, they do move either to the left or the right. And now we can look at our pressure versus position graph. So here we have the maximum pressure and the minimum pressure. So at this point, this maximum pressure here, where all the particles are kind of coming together, that's going to be maximum pressure. So that's going to line up right there. And then the minimum pressure, when all the particles are moving away from that spot, that's going to be the negative, the minimum pressure, right? And then the same thing here, maximum again, and then minimum again. Okay, so let's talk a little bit more about how to actually quantify our pressure wave. So we said before, remember we had our pressure was negative b dy dx. And then remember that y is a cosine kx minus omega t. So just plug in the derivative of this with respect to x, which we know is going to be negative ka sine kx minus omega t, right? So I just took the derivative with respect to x, the partial derivative with respect to x. So you get this, plug that right in here, and you can see we get this equation here, right? Our negative signs cancel, we get b times ka sine kx minus omega t. So that is the function that we were plotting right here, right? This is clearly a sine function. So this is our pressure as a function of position and time. And you can see also that the maximum pressure, so at this point right here, the maximum pressure is just going to be given when sine is equal to 1, which is bka. So it's going to be the bulk modulus times the wave number times the amplitude of our maximum displacement. And that's our maximum pressure that we're going to see in this tube here. All right, now let's just talk for a second about our perception of sound waves. So generally for a given frequency, you will experience it louder as the pressure amplitude increases. So a greater pressure amplitude will correspond generally with a increase in loudness. However, this also obviously depends on your health, your age. Obviously, young people have more sensitive hearing than older people. For example, you might have come across sometimes in certain areas where there are like deer or other kind of animals that eat like flowers and stuff. Some people will put a very high pitched noise maker on their property to basically keep away like deer and other things that will eat their plants. And the reason that they do this is because adults generally can't hear it. The frequencies are too high, and adults can't hear it, so it doesn't bother them. But if you have children or younger people that can hear it, they hear a very high pitched, very annoying frequency. So generally, as you get older, you can't hear high frequencies as well. Okay, so let's just do an example with what we've done so far. So here we have a sinusoidal sound wave of moderate loudness, and the maximum pressure variations are 3 times 10 to the negative 2 pascals above and below atmospheric pressure. Find the corresponding maximum displacement if the frequency is 1,000 hertz. And they give us here the speed of sound and the bulk modulus at basically sea level. And we want to find here the maximum displacement. So remember, the maximum displacement is going to be A. So we're looking for A. And then our maximum pressure and the maximum displacement were related through this formula. The P max was equal to BKA. So we're given the maximum pressure. So P max, maximum pressure variations was 3 times 10 to the negative 2. And the frequency was 1,000. We'll rewrite that as 10 to the 3 hertz. And we know the speed of sound. Okay, so we want to find A here. So the first thing we're going to have to do is find K, right? Because if we want to solve for A, we obviously need to find K first. So to find K, remember K is the wave number, and that's going to be 2 pi over lambda. So now we need to find lambda. So remember, lambda is related to the frequency and velocity of a wave through this. The velocity is equal to the frequency times the wavelength. And we have the frequency, right? And we have the velocity. So we can just solve for the wavelength. The wavelength is just going to be the velocity over the frequency. So let's just plug V over F into right here. So we get K is 2 pi over V times F, right? So I can just plug in some of those numbers and I get, let's see, 2 pi divided by the velocity is 344. And then the frequency was 10 to the 3. So just plug those into your calculator and this comes out to 18.3 radians per meter. And now we can just plug all that into this equation and solve for A. So let's just solve for A first. We get the amplitude is P max over B times K. And then just plug everything in. So P max we said was 3 times 10 to the negative 2. B was 1.42 times 10 to the 5. And then K was 18.3. So this all comes out to 1.2 times 10 to the negative 8 meters. So you can see how small this displacement is. So your ear is really sensitive to these displacements and to disturbances in the air because you can basically detect a disturbance that is like a nanometer. Okay, so now let's talk about the speed of sound. So we saw for a transverse wave on a string, we had that the velocity of that wave on the string was given by the tension divided by the linear mass density, and then take the square root of that. So that was our velocity for a transverse wave on a string. But what is the corresponding equation for sound waves? So for mechanical waves in general, we kind of have a general formula for the velocity of a wave in a medium. And it generally looks like the restoring force divided by the inertia resisting that restoring force and then the square root of that. So we can kind of think of, in the case of sound waves, The restoring force is sort of like the bulk modulus because, like I said before, it sort of measures how resistant to compression a fluid is. So that will be play the role of our restoring force. And then the inertia resisting the restoring force is like the mass. So in the case of a fluid, it's just going to be the density instead of the linear mass density. So our formula for the velocity of sound in a fluid, any longitudinal wave actually, in a fluid is going to be given by this. So it's going to be the bulk modulus divided by the density, and then take the square root of that. And now we also have a corresponding formula or similar formula for the speed of a longitudinal wave in a solid. And that's given by this, where now instead of the bulk modulus B, we have what's called the Young's modulus. It's kind of the same as the bulk modulus, but for solids. If you did this in chapter 11, you learn that. If not, you don't really need it too much. Just kind of look it up in a chart, and that's all you need to know. So I put the chart down here just so you could see this is table 11.1 in the book. So if you have a homework problem or any problem that asks where you need the either B or Y, you can just look it up in this table right here. So this is the corresponding equation for a solid. So this is the corresponding equation for a solid. Like I said, we're not going to use this too much. I don't even think we might have a homework problem on it, but I just figured I'd show you in case it pops up anywhere. All right, so let's do another example here. So here we're using we have a ship that uses a sonar system to locate underwater objects, find the speed of sound waves in water, and find the wavelength of a 262 hertz wave. So I'm sure you've all heard of sonar before. It just means that we're sending a sound wave somewhere, in this case to the bottom of the ocean. The sound wave bounces off an object, and the transmitter and receiver can measure how long it took for the sound wave to come back, and they can discern a shape out of that. Okay, so here we want to know the velocity and the wavelength, and we're given the frequency is 262 hertz. So the first thing we're going to want to do is use that formula for the speed of a longitudinal wave in a fluid. So we have V is equal to B over rho here. So we're just going to have to look up B and look up rho for water. So B for water, again, is given in a table in chapter 11. So you just have to flip to that chapter and look it up if you're doing this problem on your own. So B for water in this case is 2.18 times 10 to the 9 pascals. And then the density of water, I think you can find in chapter 12. Or you can just memorize it because water is easy. It's just 10 to the 3 kilograms per meter cubed. So that's an easy one to remember. Okay, so then just take the square root of this, and we will get that the velocity is 1476 meters per second. So we have 1,476 meters per second. So that's significantly faster, almost like 3 times as fast than it was in air, where it was only 344. So you can see that sound waves travel significantly faster in water than in air. And now we want to find the wavelength of a 262 hertz wave. So we can use our formula for velocity, frequency, and wavelength. So we'll have V is equal to F times lambda. We know the velocity, we know the frequency, so we just want to solve for lambda. So that will be V over F again. And the velocity we know is 1476, and the frequency was 262 hertz, and this comes out to 5.64 meters. So our wavelength is just 5.64 meters for this sonar machine. And now, like I said, you've all probably heard of sonar, but sonar, ultrasound, echolocation, these are all very similar things that use sound to detect objects and map things that we otherwise couldn't see. So one major thing is sonar to map the ocean floor. All of the maps that we have of the ocean floor were made with sonar, where you have a ship that just basically goes through in like a grid, sends out sound waves, tracks how long they take to come back, and it can just map out the ocean floor that way. So we can map the ocean floor. Obviously, animals use echolocation. They send out a sound wave. It hits an object, it bounces back, and they can tell how far away that object is. Bats are obviously the most famous example of that, dolphins too, And then also submarines use that as well. And now they have these really cool like live ultrasound images, basically, where you can see like a 3D shape of the baby while it's still in the womb, and you can see it in real time as it's moving. And this is all done with ultrasound. Okay, so those are some examples of how we use sound waves and how other animals use sound waves. Okay, so to find the intensity of a sound wave, remember from one of our previous lectures, we said that the intensity is the power over the area, right? Because the intensity kind of goes out in three dimensions. So we need to find the power first. And remember from, I think, our last lecture, we said that the power is equal to the force dotted into the velocity. So we don't have our sound force, but we do have our sound pressure, right? And we know that pressure, so this is power, because we've got a lot of P's here. So power is force dotted into velocity. Pressure is force per unit area from our like lecture 0, basically, our very first lecture. We said that pressure was force per unit area. And to find the intensity, we want the power per unit area. So we can basically just kind of put our force per unit area right in here, and we already have the intensity, right? We already have the power per unit area. We just divide each of these by the area, where this is now the pressure. So the power we said before, P is the force dotted into the velocity, and the velocity we know is dy dt. And we said the force per unit area here, so the pressure, so we're going to divide each of these by A. So the pressure here we knew from a couple slides ago, right? The pressure we said was negative B times dy dx. So now we have our intensity, right, because we have the power per unit area now, is equal to negative b times the partial of y with respect to x times the partial of y with respect to t, where this is the pressure and this is the velocity. So we have y. We know that y is equal to a cosine kx minus omega t. Dy, let's do dx first. We did already. We know that that's going to be equal to negative ka sine kx minus omega t. And then dy dt is going to be a times sine kx minus omega t. Then we have a negative sign because the derivative of cosine is negative sine. And then we take the derivative with respect to time in here, so we get another negative omega. So this will give us omega a, because our negatives will cancel, sine kx minus omega t. Okay, so let's plug that in here. So we get negative b dy dx is right here. So we have a negative and a negative, so that will cancel out and give us a positive. Ka sine kx minus omega t. And then dy dt we have right here. So we'll have, let's stick an omega in there. So we're going to have an omega in there from right here, another a, so this will become a squared, and then another sine kx minus omega t, so this will become sine squared. So this is our intensity, but this is the intensity at a specific moment in time. Remember, when we have this here, where we have the sign that depends on time, we want to take the time average to find the average power, or the average intensity in this case. So we're just going to replace our sine squared with the time average, so the average value of sine over a complete cycle, which we said is 1/2 from our previous one of our previous lectures. So we're just going to replace this with 1/2. And so now we get that the average intensity is bk omega times a squared. divided by 2. Okay, now we're just going to get this into a slightly different form. So I'm just going to rewrite that here. So we have the intensity is 1/2 b k omega a squared. And now let's get rid of k. So remember, the velocity of our wave can be given by omega over k. So we can rewrite k as omega over the velocity. So let's replace this k with this. So we're going to get 1/2 b omega over v times omega a squared. And now I want to replace the velocity. So I want to replace this velocity here. Remember, the velocity of the wave is also given by b over rho square root. So now I'm going to replace this velocity down here with this. So that will give me 1/2 b. I have an omega squared from here. So I have omega squared. Then I have 1 over the velocity. So that will be rho over b square root times the amplitude squared. Now I have b over square root b. So b over square root b is just square root b. And then let's see, so let's rewrite that. So we've got 1/2 rho b are both in the square root now, times omega squared a squared. Okay, so this is the final answer. This is the more common form of the intensity, the average intensity that you'll see. So I just rewrote that here. So we have the density of the fluid is rho, b is just the bulk modulus, as we said, omega squared is the frequency of the sound oscillations, and a is the displacement amplitude of the particles in that medium. Now it can also be more helpful to rewrite this in terms of the maximum pressure difference of our sound waves. So let's again rewrite this. We're going to manipulate this a little bit to get another equation for the intensity. So I'm just going to rewrite that here. We had rho times b square root omega squared a squared. And remember from a couple slides ago, we said that P max was equal to BKA. So let's replace the amplitude here with P max over BK. So we're going to replace this with this to get rid of the amplitudes that we're just talking about, the maximum pressure difference. So we're going to have rho b omega squared, and then P max, I'll leave out the max for now, BK squared. So let's just rewrite this a little bit. We've got an omega squared, P squared, B squared on the bottom, K squared here. So now you see here I have an omega squared and a K squared. And omega squared over K squared is equal to the velocity squared, right? So V squared is equal to omega squared over K squared. So I'm going to replace this omega squared and this K squared with the velocity squared. But remember, the velocity squared we can also replace with B over rho, right? Because the velocity is square root of b over rho, so v squared will just be b over rho. So I'm going to replace this omega squared and this k squared with b over rho. So I have rho times b over rho, and then I have p max squared. And then I still have this b squared in the bottom. So let me just write that a little bit more carefully. Okay, so now we've gotten rid of this and this. All right. So now I can just simplify things a little bit. So I have here, I have b squared. So that those cancel. So that gives me a square root b over b from this b in the square root here and this b left down here. So square root b over b is 1 over square root b. And then I have the same thing here. I have square root rho over rho, so that will give me 1 over square root rho. So I can rewrite all this as P max squared over rho times b in the square root, And I think I forgot my 1/2. Sorry, so there should be a 1/2 here. So let's put a 1/2 from the time average. So it's 1/2 of the maximum pressure difference squared over the square root of the density times the bulk modulus. And you can see that right here. And then you can also rewrite it this way. So, you could rewrite it any way you want. And the reason that this form is usually more convenient, because we can have a sound wave, two sound waves of the same intensity, but different frequencies and different displacement amplitudes, but they will still have the same maximum pressure Pmax. So that's why it can be a little bit more convenient to just talk in terms of the maximum pressure difference instead of the frequency and amplitude, displacement amplitude. And this here is just an excerpt from your book that I thought was interesting. So obviously we know that sound waves carry energy, right? Because we're talking about the intensity and the power output. So the average person here, when they're speaking, outputs a power of about 10 to the negative 5 watts. So that's obviously very small, especially compared to a light bulb where you have like 100 watts. So sound doesn't really carry a whole lot of energy at normal conversational levels. So that's 10 to the 5 watts for a normal conversation. And then like a loud yell will correspond to about 10 to the negative 2 watts. And then I thought this was interesting. So if all of the residents of New York City were to talk at the same time, the total sound power output would be about 100 watts. So that's basically just a light bulb. So you can see really how little energy sound carries at our normal conversational levels. All right, so now let's do another example. So what are the pressure and displacement amplitudes of a 20 hertz sound with the same intensity as a 100 hertz sound? So we want the pressure, so the Pmax, and the amplitude when we have a frequency of 20 hertz, and we're comparing that to a 1000 hertz sound. So 6.1 was the first problem that we did, and we found that the Pmax was 3 times 10 to the negative 2 pascals, and we found that the displacement amplitude was 1.2 times 10 to the negative 8 meters. So we want to find the pressure, so we want to find Pmax and A for this 20 hertz wave with the same intensity. So let's first find the intensity of our 1000 hertz wave. So our 1000 hertz wave, we'll call that I2. And let's use this formula here. So we're going to use that first formula. So we have Pmax squared is over 2 rho times the velocity. So Pmax squared we found, or the previous problem had given us, was 3 times 10 to the negative 2 divided by 2. The density of air is about 1.2 kilograms per meter squared. So I'll just write that here. So air, about 1.2 kilograms per meter cubed. So we've got 1.2 there. And this is just the velocity of sound waves in air. So that's going to be our 344 meters per second. And this is squared. So this comes out to 1.1 times 10 to the negative 6 watts per meter squared. So that's our intensity of this wave. And our first wave, our F1 wave here, has the same intensity. So since it has the same intensity and it's traveling also through air, so it's going to have the same density, right? It's going to have rho, and it's also going to have the same velocity. We can see right away that Pmax is going to be the same, right? Because if we have two waves of the same intensity traveling through the same medium, Pmax has to be the same. So our Pmax has to equal the same as for our other wave, which was right here. So that was 3 times 10 to the negative 2 pascals. So that's our Pmax. And then let's just make this a little bit smaller. So now for the amplitude, let's go back to this equation here. So we're going to use this equation to find the amplitude. So we're going to have the intensity is equal to 1/2 rho b omega squared a squared, where omega is equal to 2 pi times the frequency because we have the frequency of 20 hertz. And let's solve for a. So we know everything else. We know the intensity. We can look up the bulk modulus. Okay, so let's solve for a. So we're going to get a, let's start with a squared, is equal to the intensity times 2 divided by square root rho b omega squared, and then we're going to take the whole the square root of that to find the amplitude. So let's just plug some things in first. So we have 2 times the intensity, we said was 1.1 times 10 to the negative 6, right? Right here, because it has the same intensity as our 1,000 hertz wave. And then this is divided by square root density of air was 1.2, and the bulk modulus we can just look up in that table, and that's 1.42 times 10 to the 5. So that's the bulk modulus. And then omega squared is 2 pi times 20 squared. So you're going to plug all that into your calculator, then take the square root of all that, right? And that's going to give us 6 times 10 to the negative 7 meters. So that is our displacement amplitude. All right, now let's do one more example with intensity. So here we have an outdoor concert. We want a sound intensity to be 1 watt per meter squared at a distance of 20 meters from the speakers. If the sound intensity is uniform in all directions, what is the required average acoustic power output of the array, or just of the speakers? So we want, let's see, we have the intensity. So we want the intensity to be 1 watt per meter squared. And the distance is 20 meters. So our R will be 20 meters. And we want the power output. So remember, the intensity is the power divided by the area, which in the case of a sphere would just be 4 pi r squared. But here, the question isn't very clear, and they actually want you, they're assuming that the speakers are on the ground. So if we have a speaker on the ground here, and this is like our speaker, so our area here isn't actually going to be a whole sphere, it's just going to be a half sphere, because imagine our sound is only going through the air here if our speaker is on the ground. And we're going to ignore the fact that the sound can go through into the ground, so we're just looking, just pretend it can only travel through the air, and it's just a half sphere here. So the question isn't that clear with the assumptions they want you to make, so it'd be totally understandable if you just divided by the full area of a sphere here instead of half a sphere. But anyway, so we can calculate it for half a sphere, right? The area of a hemisphere is just 1/2 4 pi r squared. So we can just plug that in. So we just want to find the power. So let's just solve for power here. So this is actually 1/2 times 4 pi r squared. So our power will just be I times 4 pi r squared over 2. So this will be the intensity, we said, is just 1, and then 4 pi, the radius is 20 squared, which will be 400, and then divide that by 2, and we get 2,500 watts. Okay, so again, if I gave you a problem like this on the exam, I would make sure to make it clear that you're only supposed to take into account half the sphere, not the whole sphere. I don't think that this problem is that clearly worded, so I just wanted to go over that with you, because I know that there's a lot of cases where you kind of make assumptions in physics that aren't that obvious if you don't have a lot of practice. So this one I don't think is very obvious, but it basically just takes a lot of practice to know when you can make some of these assumptions that we're making and when you can't. Okay, so let's talk about decibels. So I'm sure everyone's heard the word decibel before. It just measures sound intensity. So since as we said before, the audible range of hearing is from 20 to 20,000 hertz. That's like a huge range, right? It's going basically from 10 to 10 to the 3 hertz. So that's a big range. Whenever you see like a very large range, it's usually a good idea to use a log scale. So the decibel scale is a log scale. And the sound intensity is denoted by beta here. So when we talk about the intensity of a sound, we have beta is equal to 10 decibels times the log of the intensity of the sound divided by some base intensity here. So this is usually like the threshold of human hearing. So that's given by 10 to the negative 12. I should say that's watts per meter squared. So this is just some base intensity, and then this is the intensity of that sound that you're dealing with. And the log here is in base 10. So something to be careful of is that usually when you see log, you can right away assume log base 10, but sometimes in physics we'll use log to refer to base E. So it's not always 100% obvious which base you're using. In this case, it is base 10 though. So just to review this for a second, so let's do beta is 10 decibels times log of I over I naught. This is measured in decibels. So let's say we had a sound that was at intensity I naught. So just the threshold of hearing. So our intensity was at I naught. That would mean our decibel, so beta, is 10 times log I naught over I naught, and that's going to be just 10 times log of 1, right? And remember, our log plot looks sort of like this, where this is 1 here. So the log of 1 is 0, right? The log plot crosses the x-axis at 1, and it's 0, so this is 0. So at the threshold of human hearing, we say that that intensity is 0. Okay, and let's just do one last example with the decibel scale, because I know students get thrown a little bit when we start manipulating logs. So definitely brush up on your logs a little bit if you feel rusty at all with them. So in this problem, consider an idealized bird that we're treating as a point source that emits a constant sound power with an intensity that obeys the inverse square law. So that means it's uniform in all directions. If you move twice the distance from the bird, by how many decibels does the sound intensity level drop? So we're moving from point 1 to point 2 here. So we're moving from P1 to P2. The bird has some power, we'll call P. So that will be our we'll call it P sub B for P of the bird, power of the bird. And so the difference in the intensities will be beta 2 minus beta 1, right? That's the difference in intensity. And that will be equal to 10 log I2 over I naught minus 10 log I1 over I naught. Okay, and let's simplify this a little bit so I can factor out my 10 from both terms. And then I get log, and I'm going to just expand out these fractions here. So remember, log of like a over b is log a minus log b. So I have log I2 minus log I naught from that first term. And then I have minus log I1 minus log I naught. But I have a minus sign out here, right? I have this minus sign, so that becomes a positive. And then let's simplify this a little bit. So we have 10. We can see here that our minus log I naught get cancels with the plus log I naught over here. So those two things cancel, and we're left with just log I2 minus log I1, which just gives me 10 times log of I2 over I1. So you can see here that when you are comparing two intensities the baseline intensity doesn't matter, right? Because we just picked some arbitrary baseline. So that drops out when we're comparing two different intensities. So here, all that matters is just I1 to I2, the ratio of those two. So here we said we moved twice the distance from the bird. So how do what's the ratio of I2 and I1? How do those relate depending on the distance? Well, we had that in one of our previous chapter 14, I think, where we said, let me just write another page here. So we have beta 2 minus beta 1 is 10 log I2 over I1. So the ratio of I2 to I1, remember from our previous lecture, was the radius 1 squared over the radius of 2 squared. So I can just replace this ratio with this ratio. So I get 10 log R1 squared, R2 squared. But we said that we moved twice the distance, right? So this, I can actually, since I don't know what R1 and R2 is, I can say, well, R1 squared, I don't know what that is, but I know that R2 is twice of that, right? So I can replace R2 with 2 times R1 squared, and that becomes R1 squared over 4 R1 squared. So the R's actually cancel out, right? And I'm left now with just the log of 1/4. So it actually doesn't matter what my initial radius was, right? It ends up being still log of 1/4 if I'm doubling the distance. If I started at 1 meter and moved to 2 meters, or if I started at 2 meters and moved to 4, or started at 4 and moved to 8, it doesn't matter because my ratio of the radiuses and my ratio of the intensities will end up being the same thing. So all I have to do here now is just take the log of 1/4. So the log of 1/4, since 1/4 is less than 1, that ends up being negative. And I think it comes out to negative 0.6. So 10 times negative 0.6 gives me negative 6 decibels. So that just means that this difference is negative, which I expect because I expect beta 2 to be less than beta 1 because we're further away, so the intensity will be less. And again, this is true no matter what distances you started at. So if like I said, if I started at 1 meter and moved to 2, it would be a 6 decibel difference. If I started at 16 meters and moved to 32 meters, it would still be a 6 decibel difference. Okay, so that's it for decibels, and that's also it for today. So I will see you guys on Thursday, and this is the last chapter before our midterm. So we'll finish up chapter 16 on Thursday. Next Tuesday, we'll do like a review lecture instead. I'll send out some information about that, obviously. But this is the end of chapter 16. On Thursday will be the end of our material for midterm 1, okay? So I will see you guys Thursday.